a univariate distribution, something like, well, for discrete distribution, it was a lot of them, binomial, Poisson, geometric distribution, many kind of continuous distribution, exponential, Gaussian, sorry, normal distribution, beta, gamma, so many of them. So what about now? We're talking about multivariate random variables, and so what are the specific models? And it turns out that in general, kind of there are not many of these models. So the usual approach is that if you have a multivariate distribution, so usual approach, so you build multivariate distribution from univariate. So distribution is usually built from univariate distributions. So if you have several random variables, so x1, x2, so on, xn, and you want to figure out what's the joint distribution, so model with kind of not only figure out, just model, what's the model for this several random variable. So there are usually some usual approach is to, well, maybe you can assume that they're independent. Of course, not always, but sometimes you may assume that they're independent. So, if you assume independence, then it's kind of by definition of a dependence, you can write down the joint density or joint PMF, but if we're talking about continuous random variable, then joint density. So you can write the joint density of them as a product of the marginal density, so density of every of them, kind of each of them. So you can write that this is a product of this many distributions, many densities. So this is, well, in many cases, you don't want to assume that they're independent from each other. So another approach is write down kind of them by using the multiplicative law. So if you under some assumptions, so under some assumptions, so which we will not specify in this course, just this is just for general information, how the things are usually done. Under some assumptions, you can write it as a product of the conditional probabilities. So you can write x1, xn of x1, xn. You can write that this is equal to f. So you write that you observe one of them, right? And after that, multiplied by the probability of the second one, given that you know the value of the first one, right? Given x1. So you observe the first one, and you assume that you can, in this case, you can write the conditional probability for the second one. Right? And after that, you continue this. So say write it one more kind of a way. So you write that this is equal to product. Now you assume that you observed two of them, and the third one will depend only on the second one. So you write that this is equal to the product that you multiply it by x3 given x2, and here's x3 given that you already know x2, right? So but well, in this assumption, it's the x3, if you know x2, then it doesn't depend on x1, on the first one, and kind of you do it until the last one, and xn given xn minus 1 multiplied by xn given xn minus 1. And so kind of these assumptions called that this model, the situation can be modeled as a Markov chain. So which we will not study kind of, so don't worry, kind of, it looks maybe kind of difficult, kind of, but this is one other way to model them. So the general idea is that you model the many random variables by using kind of univariate. So in the first example, it was just a product of the functions where each function depended on one random variable, right? So this is density of one random variable, you just take a product. See, here as well is a little bit more complicated, but it's also kind of built as a product of several functions, right? And it's just product, not the marginal densities, but the product of well, first is a marginal, and after that the conditional densities. Right? So now this is the usual way how you can do it in general, kind of how you model things in general, but there are some exceptions. So there are some distribution which are genuinely multivariate, and these two distributions kind of which you can use to model many random variables. It's a multinomial and multivariate Gaussian distribution. So truly multivariate distributions which we will study. So which we will talk about, not maybe in many details, but kind of in some details. So it's the first one, it's a multinomial distribution, which we will talk in a couple of minutes. Right? So this is the first one, and the second one is a multivariate normal distribution. Normal. Maybe there is a couple of more of them. One of them is called Dirichlet, kind of, which is also kind of used. But we will focus on these two distributions in this course. Okay, so you can see there are just two kind of, well, distribution compared to many distributions that we talked when we talked about univariate random variables. And okay, so now multinomial, let us talk about multinomial distributions. Right, so multinomial distribution is a generalization of binomial distribution, distribution. So multinomial random variable generalization of a binomial random variable. So let us recall what was the binomial random variable. So we had a binomial experiment. So this was a trials. So its basic example is that you flip a coin, kind of, right? Toss a coin and see whether it's a head or a tail. Right? So more generally, you kind of do trials, independent trials, something like a flips of a coin, and check whether the result of this specific trial is a failure or success. So it's a sequence of trials with two outcomes. Okay, so success and failure. In the example with the coin, you can think about kind of, well, head is a success and tail is a failure. Right? So and maybe kind of you have a parameter, so it's n trials. So sequence of n trials with two outcomes, success and a failure, and you can think about, well, kind of what's the typical outcome, right, of this trial. It will be a sequence, so something like this: success, failure, right? So So it's sequence: success, failure, say failure, success, success, and so on, kind of until there's something like one, and it will be something like n times, kind of, right? So n trials. And so this was an experiment, right? And the binomial random variable was defined as the number of successes. So binomial random variable is the number of successes. And so now we calculated what's the distribution of this random variable. So call it x, say. Right? So this is random variable x. It's the number of successes, and the distribution, so probability that x takes the value x, it was equal this guy. So it was x. So usually we call it maybe k, but let me write here x out of n, right, multiplied by p to the power of x and 1 minus p to the power of n minus x. Right? So where p is the probability of success. Probability of success in a trial. So we assume that the trials are independent from each other, and kind of the probability of success in each trial is equal to this p. Right? So to this random variable p. Then the probability that the random variable, so this is a probability that the random variable x takes value x small. Right? And what's the possible values of x small? It's x can be 0, so 0 successes, can be 1 success, and well, so on. Maximum the number of successes can be n, right? So this is kind of the possible values of the x. Right? Okay, so this is binomial random variable. So what's the kind of generalization? So the generalization is very simple. You assume that there are not two outcomes, but more outcomes, more possible outcomes. So multinomial experiment, it's n independent trials, with k possible outcomes. So let me write k possible outcomes. There, in the previous case, it was two possible outcomes, failure and success. Here it will be k possible outcomes, where k is some number possible outcomes. Right. So, and well, we can kind of number them somehow, so that we will be able to talk about them, and let us call them so we can code them. Right? So let us call it 1, 2, and so on, kind of k. And so just kind of, so I would say that this is which outcome, right? So it's 1, 2, and k, right? So in previous example, it was success would be kind of 1 and failure would be 2. And so now, and so you can write, and so that the typical outcome would be something like that. It would be something like, say, 3, 1, 2, so k, and so on, right? So kind of, and again, so n possible kind of, so you do that n trials, so you have n outcomes kind of in each trial. So this is a possible result. It's a result of the experiment. Right? And so kind of the random variable which we define in this case, well, it's not kind of failure or success. So in this case, we define kind of k possible outcomes, and we count how many times it occurred in the experiment for each of them. So xi, it will be a number of times outcome I occurred in the experiment. And so this is it. So now you can see, well, kind of in this case, there is a constraint here. So xi can take values, xi can take values. And so 0, kind of 1, so n, right, like in the previous example. So, but there is also constraint x1 plus x2 plus xk. So the total kind of how many kind of a total counts. So if you sum all counts for every possible category, right? So of the outcome, then you should get n. Right? So kind of in the previous example, it was that there was two categories, failures and success. And we basically ignored the failures. But in principle, you know that the number of successes plus the number of failures should be equal to the total number of trials. So this would be kind of, this is a generalization of them. And then after that, you can ask the question, so, okay, so what's the distribution of this vector? So x1, x2, xk. And so, so first of all, so by definition, so definition with x1, the x1, x2, xk is called the multinomial random variable, and it's joint PMF. So in this case, it's a discrete random variable. So we can talk about PMF, joint PMF. Discrete random variable takes only kind of fixed number of values. And so joint PMF, okay, so kind of let us write it. So it's px1, so xn, and it depends on n arguments. And so it's by kind of, so this is a probability that x1, random variable x1 takes value x1, and so on, probability that random variable xn takes value xn. So it turns out, well, it's, I will not approve it, kind of generally, kind of not prove much in this section. I just say that this is kind of can be proved using the same method as for the binomial random variable, that it's equal to here we'll have a multinomial coefficient. Before that we have a binomial coefficient right here, right in this formula. So this was the formula for the binomial random variable. And you will see that it's binomial coefficient multiplied by p to the power of x minus p to the power of n minus x, where p was the probability of the success, and actually 1 minus p is the probability of the failure. X here is the number of the successes, n minus x is the number of the failures. So we generalize in this formula and write that this is actually not binomial coefficient, but multinomial here. So x1, x2, xn, right? So not xn, xk here, and here's also xk. Right? So remember that k is the number of the categories. So kind of here, so here's xk. Everywhere here is xk. N is the number of outcomes. Right? So multiplying what we'll have here. Okay, so we'll have here probability that the trial ends in the outcome number 1. So we will denote this as P1. Right? So probability that the trial gives you the outcome of the category 1 to the power of x1. Multiplied by P2, it's a probability that in this particular trial you'll get the outcome 2. Multiple to the power of x2, and so on until the pk, the last possible category, to the power of xk. So where, okay, so for completeness, so here's where pi is the probability that a trial results in outcome I. So kind of in the previous example, it was a two possible categories, success and failure, and there was a two probabilities, p probability of a success and 1 minus p probability of a failure. So here there will be kind of k categories, more than that. So this is a formula for the distribution. The only thing that it's valid only if x1, xi takes value from 1 to n, right? Sorry, from 0 to n. And the sum of them, x1 plus x2 plus xn plus xk should be equal to n. Right? Otherwise, it's 0. And so maybe kind of an example. Right? So how this model can be applied. So what was the situation that this model applied? And so there are kind of simple examples. So this is a little bit more interesting example. So example. So suppose we look at the random texts. So so we look at random text, text, which consists of say 10,000 words. And so you go to some kind of internet source, to some collection of the texts, to some library, and select a random text which consists of 10,000 words. And we are interested to model the counts of the words, right? So we can kind of interested which words is the most frequent, right? How often is the word love occurs in this text? Well, kind of you can compare kind of what about kind of this specific category of a text, say poetry, against kind of a different category of a text, so prose, and you might be interested in the question, so whether the word love is more kind of frequent in the poetry than in the prose. So how we model the distribution of the different words in a random text, basically. And so now, so one problem with that is that, so if you want to take one random text and another random text, so we might have some words may be present in one text, but not in another. So this is not convenient. So, and useful kind of in this situation to define something like a dictionary of words. So something which doesn't depend on some particular text, but kind of just dictionary of all possible words. Well, dictionary of all possible words is a little bit too much, kind of, because the kind of English language contains around 1 million words or something like that. So too many words. So so you just define some kind of a dictionary of the words. Dictionary of words. And maybe kind of you specify how many of them. So maybe 50,000 and say one word, right? So with one word which is kind of reserved to indicate that the kind of something that you found in a text is not really in the dictionary. So you call it, say, unknown. Right? So this will signify something like unknown word, or kind of word not in the dictionary. And so now you kind of, so what could be an example? You can say something like a dictionary is something like that. So it's, you can list them in alphabetical order and say it would be something like that. So A, so this one word, so well, kind of say aardvark, right? Another word, say after that and, say, so maybe and, right, and so on, kind of. So you have something like a list of words and kind of say, suppose it ends with zebra. And maybe after that you add this unknown word. Right? So kind of in general, you kind of, so you define it. So you define that there is a 50,000 of these words, and there is one additional word here, unknown. Right? So that's why kind of I say that it will be 50,001 word. Right? So now, so you can now you can kind of translate every text in the sequence of numbers. So then the number will be just a kind of the order number of this word in the dictionary. Okay? So if you have a text that starts, so text starts something like an aardvark, and a zebra, and something after that, right? So kind of, right? So this is the beginning of this text, right? So you can translate it using the dictionary. You can translate, so it translates to a sequence of numbers. The numbers will be something like you look at what n. N is the number 3 in this dictionary. So you put here is 3. Right? So aardvark is the number 2 in this dictionary. So you put here 2. And is the number 4. Right? So it's number 4 in this list. So A is the number 1. Right? So and zebra is, well, it was the last one in this list, so it's 50,000. Right? So maybe kind of, well, let me omit here this, well, maybe just kind of 50,000. Right? And after that something else. Right? So this is kind of, so this is the sequence for this specific text. And so now after that, okay, so we encoded text by numbers, and we can kind of, so kind of what's the relationship, what I talked before that, what's the relationship with a multinomial distribution. So now you can, now you if you do very simplifying assumption on this model and assume that all words are independent. So assume all words in a random text are independent. It's not particularly good assumption. It's a pretty bad assumption. So kind of the words are not really independent. But for the sake of argument, let us look at the model when all words are kind of independent in a text. Right? In this case, you can say, all right, so this is the actual number of this is actually multinomial experiment. You look at the first word and see what's the result of the first trial in this experiment. So what's the, if you look at the first word, this is our first trial. So what's the result of this trial? So this is with some word. Okay? So if you look at this at the first word, the result was the word n. So the result is the kind of the number 3. And you look at the second word, this is the second trial, it was aardvark, this was the number 2, right? And so on, right? So, and you can see that this is actually a multinomial experiment. So in this case, it's a multinomial experiment. So now what's the number of the trials? Well, it's the number of words in a random text. Okay? So with in our case, we assumed that with a text, all of them have 10,000 words. Right? So Right? So now, what's the number of the categories? Right? So the number of the categories is it's the number of words, or the number of all possible words, and we assume that this is equal to 50,001. So, and k is equal to 50,001. And so this is okay. So what about the probabilities? So and pi is the probability that we observe word say code wi in as a word in some place in a particular place in the text. And so, for example, here P1 will be equal to the probability that we observe the word A, right, in a specific place in the text. And so, well, kind of, so how we can model it, it's usually kind of difficult kind of to do some theoretical estimation. And usually kind of you just can look at a very large number of text and estimate it empirically. What's the empirical frequency of this word A in a large number of the texts? Right. Okay, so so this is an example how this model in principle can be applied to kind of to modeling a real situation, right? So kind of how, so this is kind of multinomial experiment, multinomial random variable as an application to the modeling of the texts. Right? Okay, all right. So now kind of what's the properties of this random variable? So properties of the multinomial distribution. Normal distribution. And so when we talk about the multivariate distribution, we will usually talk about the marginal distributions, right? Maybe about conditional distribution and well, kind of expectation of every kind of single kind of random variable, right? And so if you're talking about kind of, so you have here x1 and xk. So we can look at one of them, each of x1, xk separately and say what's the distribution of each of them separately. So this is looking at the marginal distribution. So in principle, we can look also on the conditional distribution. Maybe we will not do it in this specific case, maybe kind of will do, kind of say something first. So marginal distributions, which is kind of every one of them. So conditional, it means what, suppose we observed that x1 is equal to something. What you can say about other random variables in this selection, about x2, xk, if you know the value of x1. So conditional distributions. And maybe kind of something like a variance, which is kind of, well, particular case of these two things, simplified version of this. All right, so what's the theorem here? So now, if you look at this, so if you look at on the random variable xi, right? So what's the marginal distribution of them? So you can think about xi. So it's a counts of the outcome of a category I. So kind of it's useful to think about our previous example as a general kind of example, right? So xi is the counts of a word I, right? So if you want to figure out it, well, you can think about, so you observe xi, it's a success. If you observe the word I, it's a success. If you observed any other word, it will be a failure. Right? So now xi, from this point of view, xi is just the number of a count of the successes, the number of count of the cases when you observed the word I. Right? So an observation of all other variables are failures, so it's a binomial random variable. So xi is kind of more or less kind of just from this argument follows that xi is a binomial random variable with parameters n, so number of trials, and p equal to pi. And so just you start to ignore all other possible categories of outcomes. You just look at this kind of category I, and all other it's a failures. If you observe category I, it's a success. Right? So the probability that it will happen is pi. So it's not kind of, it's all obvious, I think so. But if you know that it's a binomial random variable, you can write down that's the variance. So what's the expectation and the variance of this thing, right? So expectation of xi, well, it's equal to, okay, so n pi. So in our example, so if pi is a probability that you observe, if p1 is a probability that you observe the word a, right? So article a. Right, so here's a p1 actually should be, right? So what's the expected number of a of these words a in the text? It's n multiplied by this probability of p1. Right, so now what about variance? Right, well, again, so by our previous result, that this is equal to n pi 1 minus pi. Yeah, so this is the first thing that we can say. Now, the second thing, so we can ask the question, so suppose that we observed so the second thing, suppose it's something like the conditional probabilities, but before the conditional probabilities, maybe ask the question about, well, what's the covariance of xi and xj? Right? So suppose that we're looking at the covariance xi and xj. Right? And it turns out that this is equal. So now we can guess actually the sign of this. So if I observed very many outcomes of the type I, right, then in this case it's likely that the counts of the outcomes of the type J is small. Right? So because if you observe very many words of one specific word, then the probability that you observe a different word will be smaller, a little bit maybe, but smaller. Right? So it will be negative, and it turns out that it's equal to n pi pj. Right? Right? And so this is maybe kind of useful to prove, kind of, because it's not, it's kind of, well, kind of intuitively clear it should be negative, but the formula is not obvious, right? And it is possible to prove it, kind of, not very difficult to prove it. So maybe kind of let us postpone it a little bit, right? The proof of this formula. So, and let us look at the another thing that we can say about this random variable. So suppose that you want to figure out what's another thing. So suppose that you're looking at the random variable y, right? And this is the sum of the counts for some of the types. Right? So you can look at something like what's the y is equal to x1 plus say x3. Right? So now if you look in our example, this would be something like it. In our kind of example here, x1 is the count of the words a, right? So in the text. x3 is the count of the words n in the text. So y here, right? It's the sum of x1 plus x3. It's the sum of the outcomes of the type of the words a and n. So it's kind of right. So here's it's equal to the counts of the outcomes, sum of the counts of the outcomes of type 1 and type 3. So now we can ask a question, what's the distribution of y? And if you think about this, it's just kind of, it's also binomial random variable, right? So it's a counts of the outcomes of type 1 and type 3. So you can think about if you observed outcome and it is either of type 1 or type 3, then it's a success. If it's anything else, it's a failure. Right? And you count the number of successes, the number of times that you observed either outcome of type 1 or that outcome of a type 3. Right? So you count the number of successes in a binomial experiment, essentially. Right? So you can see that y is a binomial random variable with parameters so what's the parameter? It's what's the probability that you observe the outcome of type 1 or of type 3. This is the sum of the probability that you observe the outcome of type 1 plus the probability that you observe the outcome of the type 3. So it's the parameter is a p1 plus p3. So maybe n, and so this is a p3. So this is the probability that you observe that you'll have a success in this binomial experiment. It's so clear, right? Okay. And so now, well, kind of this can be generalized, and we'll have another theorem which says that, well, kind of if y is equal to the sum of x j, where j belongs to some set S, right? Then y is binomial with parameters n and p equal to the sum of this pj where j belongs to S. It's the same thing like here. I just kind of I try to write it a little bit more generally, right? So if you sum not just two random variables x1, x3, but maybe x1, x3, and x5, right, then in this case the result will be binomial random variable with the parameter n and the probability kind of parameter p equal to sum of p1 plus p3 plus p5. So kind of it's just kind of generalization of this observation. And again, so this is more or less clear, right? So kind of it's clear theorem. All right, so now let us, if we have this theorem, right, so let us try to prove a previous theorem. So here was a theorem, say kind of 1, which was more or less obvious. Theorem 2, which is not obvious, and this is theorem 3, right, which is also kind of more or less obvious. And so let us, the only thing which is not clear is this theorem 2 about the covariance. So let us try to prove it using theorem 3 and theorem 1. So now let us do it this way. So proof of theorem 2. So in the lecture notes, I did it a little bit differently, right? So kind of than here, using indicator random variables. So now let us try to do it a little bit differently, kind of, right? So let us write what's the variance of xi plus xj, right? And so, well, kind of, so we just said that by theorem 3, right? So it's a variance of a random variable, which is a binomial, right, with parameters n and parameter p equal to pi plus pj. So the variance of this will be n. Here's pi plus pj multiplied by 1 minus pi minus pj. So because this is a binomial with parameters pi, so n and p equal to pi plus pj. So this is a variance of a binomial random variable with these parameters, right? So on the other hand, we can write it, okay, so it's a variance of the sum of the two random variables. And we studied just kind of recently kind of how to calculate the variance of the sum of the two random variables. We know that it should be equal to the variance of xi plus variance of xj plus 2 covariance of xi and xj. And okay, so by theorem 1, we know that xi is a binomial random variable with parameter pi. Xj is a binomial random variable with parameter pj. So we can write their variances. So this is n pi 1 minus pi. And this one has a variance n pj 1 minus pj. And this is, well, we don't know kind of, but this is what we want to calculate. Right? So now, but now we can calculate it because we know that this variance, it's equal to this quantity here, right? And it's equal to this thing on the other hand, right? So, well, we can say that, okay, so then we have 2 covariance of xi, xj is just equal to, okay, so this n pi plus pj 1 minus pi minus pj minus this part. Okay, so n pi 1 minus pi minus n pj 1 minus pj. Right? And you can, if you see kind of here in this expression, you'll see n pi 1 minus pi. This will cancel out. Then there'll be n pj okay, so this is probably needed to be calculated. So let us calculate it, what will happen in this case. So there will be n pi plus pj, right, minus n pi so maybe kind of, so let me kind of, so just kind of, let us write it systematically. Okay, so it's equal to n pi, so this pi multiplied by 1 minus n pi squared, so we multiply it by pi, minus n pi pj, right? So this is pi multiplied by this pj, minus n pj, sorry, plus n pj, so this is pj multiplied by 1, minus n pj pi, minus n pj squared. Right? So this is the first expression, and the second one is n pi plus n pj minus n pj plus n pj squared. Okay, so here's, sorry, minus n pi okay, so here's, sorry, the first one minus n pi plus n n pi squared, and the second n pj plus n pj squared. So now we'll look what we can cancel out here. So this thing cancel out, n pi squared cancel out with this thing. So here, so I need to write a little bit more accurately. So npj cancel with this thing, this npj cancel with this thing. So what remains is these two pieces, right? So it remains that it's equal to minus 2 n pi pj. Okay, so and well, kind of if we cancel with 2 here, then we will get that the covariance of xi and xj is equal to minus p n pi pj, right? Which is what we wanted to prove. And so this is the theorem 2, the statement of the theorem 2. Okay. All right. So maybe we'll make a break here. Right? So kind of, right. And after that, we'll talk a little bit more about this multinomial distribution, maybe give a couple of examples, and maybe another theorem about the conditional probabilities. All right, so small break for 5 minutes. All right. So let's restart. And okay, so the last thing which I want to formulate is a theorem about the conditional distribution. It's very useful. I'm not sure it's in the book, but it's typically useful thing. So this theorem, so this is our theorem 4. Here will be, so suppose so that x1, x2, xk, it is a multinomial random variable with parameters p1, p2, pk, and n. So n is the number of the trials, right? So, and p1, p2, pk is the probability that the trial results in the outcome number. So 1, 2, or k. Right, and so now we assume that so you know that we observed that one of these outcomes. So here, so let us say k. So assume that xk is equal to x small k. Right? So what is the so, well, kind of the question, so I'm formulating the theorem. So the question is, what's the conditional distribution of hours? So you observed one of them, so you know that the, say, one specific word occurred xk times. Right? So occurred xk times. So the question is, what about how it influenced the distribution of hour counts of the words? And it turns out that in this case you can write down you know that the conditional distribution of the remaining counts, it's also multinomial. So then the conditional distribution of x1, x2, xk minus 1, right? So those that you don't know, it's also multinomial, but you need to say what's the parameters of this thing. And the parameters, well, one of them is the kind of number of the trials which remains for this x1, x2, xk1, and you already know that there are the xk. So this is the number of times that the trials resulted in the outcome of type k. Right? So the outcome of the type k. Right? So all other outcomes have a smaller number of possibilities. So they should sum to n minus xk. Right? So because, well, xk already occupied. Right? So so this is one parameter. So with parameters, this is trivial, that the one parameter is n minus xk. But what about the probabilities? Right? Before that, the probabilities of the outcome 1 was p1, the probability of the outcome 2 was p2, right, and so on, pk minus 1. But now they cannot be kind of like that because they don't sum to 1. Right? So they are sum to something smaller than 1 because one of them is missing. The pk is missing. And so so in the simplest thing that you can do is just normalize it, the divide by the sum. And it turns out that this is a correct thing. So it's equal to p1 divided by the sum of p1 plus so on plus pk minus 1. And here's p2 divided by p1 plus, say, pk minus 1. And the last one is pk minus 1 divided by p1 plus plus pk minus 1. And so you just kind of take this p1, p2, pk1, so which were probabilities that you observed with specific categories. And so in before that you observe these particular categories in a trial. Right? And you divide it, well, now, well, kind of they don't sum to 1, you just normalize it. So divide by some number, some which such that we sum to 1. And then this is kind of there. So we will. I'm not going to prove this theorem. Well, kind of just proved by definition. So what's the conditional PMF and kind of right. So right from the definition. And so now let us look at an example of all this stuff. Application of this some simple example, not about words, but simpler than that. So example here will be kind of that there are 3 card players with different skills. So player 1 wins. So if they play together, right, and so there are 3 players, so they play together a game, and so player 1 typically he wins a. So let me see what parameters I use here. Player 1 wins 20% of the time. So player A, say, we call it player A wins 20% of all games. So now player B, so he wins 30% out of all games. So player C 50% out of all games. Right? So and suppose they play a sequence of n equal to 6 games. And so now the first question, okay, so the first question is very simple. So what's the probability that A win 1 game? So probability that A wins 1 game, B wins 2 games, and C wins 3 games. And so now if you look at this, you realize that this is a multinomial random variable, because you can have a sequence of 6 games, and game can result in a win by 1 person. So the first game, if the person A win, well, this is outcome of type A. Okay? So you have a typical outcome will look something like that: A, B, C, 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 say B, something like that. Right? So this is kind of 6 games, and these are outcomes A, B, C, 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 and B kind of. And well, you count the number of the outcomes of each type. So essentially what you are interested to know is that what's the kind of say XA is number of games won by player A. And you also have XB, something like it's won by player B. Right? So kind of XC. Number of games won by the player C. So now with 2 free random variables, so XA, XB, and XC. So this is a multinomial random variable with parameters. Okay, so n is equal to 6, so total the number of kind of games is 6. So this XA plus XB plus XC should sum to 6. And another parameter, so PA is equal to, okay, 10%, sorry, not 10, 20%, 20% P B is equal to 30%, and PC is equal to 50%. So we kind of, you look at this one particular game, when with probability 20% where player A wins, with probability 30% player B wins, and with probability 50% player C wins. Right? So kind of, so now, okay, so what you're interested in is just a probability that XA is equal to 1, XB is equal to 2, and X C is equal to 3. So this is our XA, this is our XB, and this is our X3. So we just XC, sorry, should just plug it in the formula and get the answer, right? So we'll get that this is equal to 6. Multinomial coefficient here is 1, 2, 3. Right? So remember that this is 6 factorial divided by 1 factorial, 2 factorial, 3 factorial. Right? So multiply by PA to the power of XA, so 0.2 to the power of XA. XA is our case is equal to 1, so 1 multiplied by 0.3 to the power of XB, so to the power of 2, multiplied by PC, so 0.5 to the power of 3. So this is just kind of the answer. We can calculate it, happen that I calculated, it's equal to 0.135. So this is the probability of this thing. And we can ask other question about this. So one question could be kind of what's the covariance between XA and XB. Right? So what's the covariance of XA and XB? Right? And you can see that, all right, so it's if player A wins more games, then it's likely that this is influenced negatively, kind of XB. Kind of if XA is large, then XB kind of tend to be small, right? So in our theorem states that this is equal to minus n, so it's equal to minus n multiplied by PA, PB. And so it's equal to, in this case, minus 6 multiplied by PA is 0.1 multiplied by 0.2 multiplied by 0.3. And so, and this is equal to something. Right? And so now we can, well, this is covariance, but covariance doesn't say us much about kind of what's the real strength for the dependence. So you can ask the question, what about the correlation, kind of a correlation of XA and XB? Right? And in this case, it's equal to covariance of XA, XB divided by the variance of XA, variance of XB, but you'll need to take a square root of this. Okay, so now we calculated the covariance. Covariance is given here. Well, kind of we want to calculate the variance. It's easy, kind of. It's variance of XA. And so, okay, so we look at again. So our theorem 1 say XA is a binomial random variable. Right? It's clear, kind of. If you just look at it as kind of it's a count of the successes from the point of view of a player A. Okay, so, and the variance is equal to n PA 1 minus PA. Okay, so in this case, it's equal to 6 multiplied by 0.2 multiplied by 1 minus 0.2, so 0.8. So, and the same thing for the variance of XB. So it will be equal to 6 multiplied by the probability that B wins, so 0.3 multiplied by 0.7. And then so correlation in this case will be equal to minus 6 times 0.2 times 0.3, right, divided by square root of right, 6 times 0.2 times 0.8, right, this thing, multiply by 0 times 0.3 times 0.7. Second thing, and you can see kind of that 6 actually cancel out here, so 6 doesn't matter here. Okay, so you can figure out what's this correlation from this data. So again, so this is that I would not calculate it, but you can do it. And so okay, so this is an illustration how you apply the theorem 1 and about that XA and XB are binomial random variable, and how you apply the theorem number 2, that the covariance of XA and for calculation of the covariance XA and XB. So what about theorem 3, which says kind of about the sum? So you can ask the question, what's the what is the probability that A and B win more games together, right, than C. And so so we are looking about the situation when A and B form a coalition, they pool their money, and so we ask the question, what's the probability that we together win more games than C alone, right? So this is a question, what's the probability that XA plus XB greater than XC? But if you think about this, you'll know that XA plus XB plus XC should be equal to 6. And so so if you know XA plus XB, then you'll know what is XC. So this is actually equal to the probability that together they will win more than 3 games. Right? So it's a probability that XA plus XB greater than 3, right? And also equal to the probability that XC is smaller than smaller than 3. And so you can never calculate this probability because you know that XC is a binomial random variable, or you can kind of use the first approach. So kind of in this case, so kind of the second is clear. XC is a binomial, so it's easy to calculate. So suppose you want to use the first probability. So you know that XA plus XB is a binomial random variable with p equal to 0. So p is equal to PA plus PB, so it's equal to 0.2 plus 0.3. So equal to 0.5. So you so this is a kind of equal to the probability that this binomial random variable with these parameters, binomial random variable with parameters n equal to 6 and p equal to 0.5 is greater than 3. Right? And well, you can kind of figure it out because you know how to calculate these probabilities. Right? So, okay. So because it's univariate random variable, so it's either kind of use the tables or go to the kind of R package and calculate it. And so this is illustration how you can calculate this kind of this probability. So another kind of equation. What about theorem 4? Kind of how would theorem 4 works in this situation? So you might ask the question, so something like that one. So given that player A won 2 games, what is the probability that player B won 3 games? Right? So now how you calculate it, right? So kind of, so formally it says something like that. What probability that x b is equal to 3 given that x a is equal to 2. And so now if you kind of look at theorem C, it says that given that xa equal to 2, random variables xb and xc are multinomial with parameters okay, so what's the parameter here? So we know that A won 2 games. So the remaining parameters, so new parameter n, so n prime, it was 6 games and now 2 are gone. So it's 6 minus 2, so it's equal to 4. Okay, so now, and then now the new parameter. So what about the probability B, kind of prime, new probability of B, right? And probability of C, new probability of C. And kind of, you know that this is equal to P of B divided by the PB plus PC. And this is equal to PC divided by PB plus PC. So it's old probabilities of the win, right? But, well, they don't sum to 1. So you'll need to kind of normalize it with, so that they sum to 1. Right? So now in our case, it's equal to PB was equal to 0.3, and now you divide it by 0.3 plus 0.5, right? So which is equal to 3/8. Right? And so this is the first one, and the second one is equal to PC divided, so PC is 0.5 divided by 0.3 plus 0.5. So it's equal to 5/8. So new probabilities is 3/8 and 5/8. And then kind of in this case, it's just 2 outcomes. If it's 2 outcomes, the multinomial random variable, it's actually binomial random variable. So one of them is you can identify it with the successes and another with the failures. And so in this case, you say, all right, so it means the conditional distribution of xb given that xa is equal to 2, right, is binomial with parameters n. So prime, it's a new n, it's equal to 4, and P of B, again, prime is equal to this 3/8. And so kind of, and so you can calculate that probability that xb is equal to 3, given that XA is equal to 2, okay, so just kind of write down the formula for, you can write software or tables, but the formula would be just that this is equal to 4, it's a new n, and you take a kind of, this is what you're interested, it's 3 out of the 4, and here's p, so p b prime to the power of 3, and here's 1 minus pb prime, it's a new probability to the power of the n, so new n, 4 minus 3. So it's equal to 3 out of the 4, and here's the 3/8 to the power of 3 multiplied by 5/8 to the power of 1. Right? And you can calculate it, it will be equal to something. And so here's how you calculate the conditional distribution. Well, given that you already know some information, what happened in the game, kind of, so you know now that A won, kind of, you know that he will not win more than that. Right? So that in this sequence of game, the A won exactly 2 games. Right? So it's not. Right? Yeah, so this is an illustration of all these 4 theorems in action. And then, well, it's the multinomial distribution is pretty useful, kind of, and it's frequently used in modeling. So kind of, it's a useful distribution. So next time, what we are going to do is to talk about another very useful distribution, multivariate Gaussian distribution. So the difficulty with the multivariate Gaussian is it's usually kind of, it's much easier to explain if people know linear algebra well. And so because, well, kind of, it's much easier to write down using matrices. Otherwise, formulas become very, very kind of big. Right? But still, we will try to talk about a little bit the bivariate normal distribution. First without using linear algebra, and after that maybe I'll tell a couple of words about how this is written down using the matrices notation. So this is what we are going to do next time. Maybe we will start also next chapter after that. All right, so that's it for today. So if you have a question, so you're welcome. Otherwise, have a nice day. Thank you for being here. So see you on Friday.
Thank you, Professor.
Thank you. Have a nice day.
You too.